Welcome to the deep dive. We're here to turn complex stuff into, well, clear and maybe even surprising insights.
That's the plan.
Today, we're really digging into how integration gets applied. We're pulling ideas from a pretty standard calculus text, Stewart, Clegg, and Watson.
Right, chapter 8.
Yeah, and it's not just about the formulas, is it? It's about seeing how calculus actually lets us solve real problems, things you see around you.
Exactly. It's quite amazing how this one core idea, integration, just branches out. It tackles this huge range of challenges.
So what's our goal here?
Our goal is basically to break down these applications, make them accessible step by step, hopefully give you those aha moments without, drowning you in theory.
A shortcut to understanding how integrals go beyond just areas.
Precisely. Moving beyond areas and volumes to solve actual problems in science, engineering,
Mm-hmm.
even economics and biology, as we'll see. Connecting the dots, really.
Okay, let's start with something concrete. Imagine you've got, a piece of cooked spaghetti on a plate, a wiggly curve. How do you measure its exact length?
Yeah, a ruler won't quite cut it, will it?
Definitely not. And that's the first big idea here, right? Arc length, finding the precise length of a curved path.
It is. And the way mathematicians figure this out is, well, pretty intuitive when you break it down.
You sort of chop it up.
Kind of. You approximate the curve with lots and lots of tiny straight line segments. Think about measuring a circle by drawing a polygon inside it with more and more sides.
Right, the more sides, the closer it hugs the circle.
Exactly. That's the core idea. And in calculus terms, we make those segments infinitesimally small and sum them up using an integral.
So that whole approach, approximate with small bits, sum them, take the limit, that's fundamental.
It's the heart of integration, just like when we first defined area or volume. So for a curve way of x, the formula ends up being LEA bs squared t 1 plus x 2 dx.
Okay, let's unpack that a bit. fx is the derivative, the slope.
The slope of the tangent line at each point, yeah.
Mm.
And that whole square root thing, square 1 plus f coord 2. That's basically the Pythagorean theorem.
Ah, like a2 plus b2 plus c2.
Exactly. For an infinitesimally small segment of the curve, think of a tiny right triangle with horizontal side dx and vertical side di. The hypotenuse is the tiny bit of arc length. ds2 dx2 plus dsd. Divide ds2, take the square root, and you get that term inside the integral. You're summing up all the tiny hypotenuses.
Got it. Summing tiny hypotenuses. Makes sense. Any cool examples?
Oh, definitely. The Gateway Arch in St. Louis. Its shape is defined by an equation involving hyperbolic cosine,
Okay.
and its exact length calculable using this arc length formula. It's a real-world structure designed with this math.
That's pretty amazing, but hang on. You get this formula, but are the integrals always easy to solve? I remember some integrals being tricky.
That's a very important point. You're absolutely right. Sometimes, even with the formula, finding an exact answer, an antiderivative, is incredibly hard or just impossible with standard functions.
So what happens then in the real world for engineers?
Great question. They turn to numerical methods. Things like Simpson's rule or other approximation techniques. You can get extremely accurate answers, even without a neat formula. It's standard practice.
Okay, so we can approximate if needed. Now, you mentioned finding the length between 2 points. What if I want to know the length from the start point up to any point along the curve?
Now you're talking about the arc length function.
A function.
So it gives you a running coordinate.
Exactly that. Sx, S, Sx6t, 1 plus ft2 dt. See how the upper limit is x? As x changes, Sx tells you the length accumulated from the start, A, up to that x.
Useful for tracking something moving along a path.
Absolutely. Or parametrizing the curve itself based on how far you've traveled along it. And its derivative, ds dx, is just that square root term again. Square root a2, 1 plus fs2.
Which connects back to that ds2 plus ds2 idea.
Precisely. It all ties back together. Simple geometry scaled up through calculus.
Okay, that's arc length. Now you mentioned spinning things. What happens if we take that curve and rotate it around an axis? We get a 3D shape. We do. A surface of revolution. Think like a vase or a lampshade or a dome.
And how do we find the surface area of that shape? Not the volume, but the area of the curved skin.
Right, surface area. We use a similar strategy built from simple shapes. A cylinder surface area, if you unroll it, is just a rectangle, right? Circumference times height.
Yeah, 2 times h.
And a cone, if you flatten it, becomes a sector of a circle. So for a more complex curve, we imagine rotating those tiny straight line segments we use for arc length.
Okay.
When you rotate a little segment, it sweeps out a thin band. It's basically a frustum, like a cone with the tip sliced off.
A okay, like a lampshade section.
Exactly. We figure out the surface area of one of those tiny frustums, which involves its slant height, that's our little bit of arc length, the base, and the average radius it's rotating at.
Ah, so the radius comes into play.
Definitely. If you rotate around the x-axis, the radius for a point, x, y, is y. So the surface area integral becomes s2ids. If you rotate around the x-axis, the radius is x, so it's s2x ds.
So it's like integrating the circumference, 2π or 2x, along the arc length ds.
That's a perfect way to think about it. You're summing the areas of infinitely many thin ribbons wrapped around the curve as it spins.
Okay, that makes sense. But I remember hearing about something weird here. Gabriel's horn. Something about infinite area.
Ah, yes. Gabriel's horn, or Torricelli's trumpet, it's a classic. You get it by rotating the curve y equal 1x for x from 1 to infinity around the x-axis.
Okay, so it stretches out forever.
It does. And the weird part is the volume integral converges. It has a finite volume. You could theoretically fill it with a finite amount of paint.
But...
The surface area integral diverges. It goes to infinity.
Wait, what? Finite volume, infinite surface area? How is that even possible?
It messes with your intuition, right? You can fill it, but you could never paint the inside surface.
Mm.
It takes an infinite amount of paint. It's a fantastic example of how calculus deals with infinities in ways that aren't obvious.
Wow, okay. That's mind-bending. But surface area calculations aren't just for paradoxes, right? They have practical uses.
Oh, absolutely. Designing antennas, satellite dishes, domes, cooling towers, even calculating the surface area of a sphere uses this principle. It's fundamental engineering.
Right. Okay, shifting gears slightly. Let's talk physics and engineering. Forces, balance. Things like water pressure. How does calculus help with the force on, say, a dam?
This is crucial. Pressure increases with depth. P, frog or dead. If you have a horizontal surface submerged, the pressure is constant, and force is just pressure times area. Simple.
But a dam is usually vertical or sloped.
Exactly, so the depth changes. The pressure isn't constant over the whole surface. What do?
Integrate.
You got it. We slice the dam face horizontally into thin strips. On each strip, the depth is almost constant, so we can calculate the pressure and then the force on that tiny strip, pressure x area of strip. Then we integrate, sum up the forces on all the strips from top to bottom.
So it accounts for the increasing pressure as you go deeper.
Precisely. Allows us to calculate the total hydrostatic force the dam needs to withstand. Same idea applies to submarines, aquarium walls, anything submerged vertically.
Makes sense. Now, related to forces is balance, like balancing a tray. The center of mass or centroid?
Yes, the center of mass, the point where an object would balance perfectly. For simple point masses, it's like finding the average position weighted by the mass.
Okay.
Calculus extends this to continuous objects, like a flat plate, a lamina. If it has uniform density, we call the balance point the centroid. We find it using integrals.
How does that work?
Think about moments. A moment is like the tendency to rotate around an axis. It's force times distance, or in this case, mass or area times distance. To find the x-coordinate of the centroid, x bar, you calculate the total moment but the y-axis and divide by the total area.
And that involves an integral?
Yes. X bar equals 1a,
Right.
a bx s x dx for a region under y fx. You're essentially integrating the contribution of each vertical strip's area multiplied by its distance x from the y-axis. It's a weighted average of the x values.
And similarly for the u-coordinate, y bar.
Yep. Y bar 1a dab 12 fx active x. Here, 12x represents the average height or y value within that vertical strip conceptually. Again, a weighted average giving you the balancing point.
Okay, so integrals find the balance point. Cool. But you mentioned a shortcut earlier, Pappus's theorem?
Ah, yes.
Yeah.
A beautiful, almost magical theorem. Pappus of Alexandria figured this out way back. Connects centroids and volumes of revolution.
How so?
It says, the volume of a solid formed by rotating a 2D region is equal to the area of that region multiplied by the distance traveled by its centroid in one full revolution.
Whoa. So if I know the area and where the centroid is.
You can find the volume without doing a disk, washer, or shell method integral. Just area times 2 times the distance of the centroid from the axis of rotation.
That sounds way easier. Example.
Classic is a torus, a donut. Rotate a circle of radius r, whose center is r units from the axis. The area is fr2, the centroid is the center which travels 2r. So the volume is r2, 2r, 2rr. Done. Pappus makes it simple.
That is elegant. Wow. Okay, so we've seen physics, engineering, but the chapter also touches on economics and biology.
It does. Integration is surprisingly versatile. Economics, ever heard of consumer surplus?
Vaguely. It's like the extra value consumers get.
Sort of. It's the difference between what consumers would have been willing to pay for something, based on the demand curve,
Yeah.
and what they actually pay, the market price.
Okay.
That difference, summed up over all the units sold, represents a net benefit to consumers. And guess what? It's calculated as the area between the demand curve and the price line. An integral again, A to SP, AUX, PD, E, A to X, P, DX, quantifying market benefit.
Huh. Never thought of it as an area. Interesting. What about biology? Blood flow?
Right, blood doesn't flow at the same speed throughout a vessel. It's fastest in the center, slowest near the walls due to friction. This is called laminar flow.
Okay, like layers flowing past each other.
Exactly. To find the total flow rate, we need to account for this velocity difference. We imagine the blood flowing in thin concentric cylinders or rings. We calculate the flow in each thin ring, velocity at that radius times the ring's area, and then integrate it from the center to the wall.
Summing up the flow in all the layers.
Precisely. This leads to Poiseuille's law, F, PR4, ADL. Notice the R for the radius to the fourth power.
Wow, fourth power.
Yeah. It means a tiny change in the radius of an artery has a huge impact on blood flow. A little bit of narrowing makes the heart work much, much harder. It's a critical relationship in physiology.
That's dramatic. And the heart itself, how do they measure its output?
Cardiac output, the volume of blood pumped per minute. One common way is the dye dilution method.
Dye. They inject dye.
A harmless indicator dye, yes. A known amount A is injected quickly into the bloodstream, usually near the heart. Then downstream, the concentration CT of the dye is measured over time as it passes by.
Okay, so you get a concentration curve, rises, then falls as the dye washes out.
Exactly. The total amount of dye A must equal the flow rate, F times the integral of the concentration over time.
Yeah.
So F QAs 0 T CT dt. The integral gives the area under that concentration curve.
So by measuring that area and knowing how much dye you put in, you can find the flow rate, the cardiac output.
That's it. A direct application of integration in medical diagnostics. Pretty clever.
Definitely life-saving math. Okay, one last area mentioned, probability. How does integration fit into randomness? It seems different.
It does seem different, but it's fundamental for continuous random variables. Things that aren't just countable outcomes, but can take any value in a range like height, weight, temperature, or waiting time.
Right, not like rolling dice, which has specific outcomes.
Exactly. For continuous variables, we use a probability density function, or PDF, FX. The key idea is that probability isn't a value in a point, but rather the area under the PDF curve over an interval.
Area again. So the probability that someone's height is between, say, 170 centimeters and 180 centimeters.
Is the integral of the height PDF from 170 to 180, PAXB if you're up, DE if you have B if you have PF.
And the total area under the whole PDF curve must be
100%. Because the probability that the value falls somewhere is certain. And the function FX itself must always be non-negative. Can't have negative probability.
Makes sense. What about averages, like average waiting time?
The average value, or mean, of a continuous random variable is calculated using an integral too. It's denoted by mu.
And how's that work?
It's a weighted average, much like the centroid calculation. Me plus infx dx. You're weighting each possible value x by its probability density fx and summing, integrating over all possibilities.
Ah, so it connects back to the centroid idea.
It does. If you made a physical shape matching the PDF curve, it would balance perfectly at the mean curve. This also explains why the average waiting time might feel off. A few very long waits can skew the mean higher, even if most waits are short.
Got it. And the most famous PDF must be the bell curve.
The normal distribution, absolutely. It shows up everywhere. Heights, measurement errors, test scores like IQ.
What defines a specific bell curve?
Two things. The mean, which is the center peak, and the standard deviation, sigma, which measures the spread.
Spread, like how wide the bell is.
Exactly. A small sigma means the data is tightly clustered around the mean, a tall, narrow bell. A large sigma means it's spread out a short, wide bell.
And finding probabilities, like the percentage of people with IQs over 130.
That's an integral of the normal distributions PDF from 130 to infinity. Fun fact, that specific integral doesn't have a nice simple formula.
Oh. So how do we calculate it?
We rely on tables or computers using numerical methods again.
Right.
Calculus gives us the framework, defines the area we need, but often computation finishes the job. It shows how theory and practical calculation work together.
Wow. Okay, what a tour. We went from measuring curves
To calculating forces on dams,
understanding blood flow,
consumer economics,
and even predicting probabilities with bell curves.
yeah,
It really drives home that integration isn't just some abstract mathematical exercise. It's like a Swiss Army knife, isn't it?
that's a great way to put it. This deep dive really shows how integral calculus gives us the tools to quantify, model, and understand just so many different parts of our world.
It's not just theory, it's a seriously powerful toolkit.
Absolutely. And if you connect it all back, the bigger picture is always that same fundamental idea. Break down complexity into tiny, manageable pieces, sum them up, and take the limit. That core strategy unlocks all these diverse applications.
From the infinitesimally small to the grand scale.
Precisely. So maybe a final question for you listening. Given just how widely applicable this is, what other parts of your life or the world around you do you suspect might be secretly running on the hidden engine of integration? Something to think about.
Definitely something to ponder. Keep exploring, keep questioning.
Keep diving deep.